Need extra money for college? ISL Education Lending Scholarship Program provides $1,000 for college expenses. Registration is easy and no essay is required. Visit www.iowastudentloan.org/register to learn more. The scholarship is open to Iowa residents who are in high school and college students, as well as parents of those students. Register by November 30th for your chance at one of the 45 awards at www.iowastudentloan.org/register.
Salutations, my fellow food lovers. This is Chef Mark here from Johnny's Italian Steakhouse, and I want to tell you about our filet Oscar. This premium filet is topped with Johnny's lump crab cake, grilled asparagus, and our signature béarnaise sauce. But the start to any great night always begins with a killer appetizer, and I recommend trying out our jumbo pan-seared sea scallops with Brussels sprout slaw tossed in Johnny's hot bacon dressing. It is so good. I know that you will love my filet Oscar as much as I love preparing it, so come to Johnny's tonight. Johnny's Italian Steakhouse, Village Point Shopping Center, Omaha.
This is SpaceTime, Series 24, Episode 14. Coming up on SpaceTime, exploring the depths of Titan's largest sea, a new idea about the birth of the solar system, and the first Atlantic splashdown of the CRS Dragon cargo ship. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that Kraken Mare, the largest sea on the Saturnian Moon Titan, is at least 300 metres deep, and that's deep enough for a future automated submarine mission. Beyond deep, Kraken Mare is also immense, nearly the size of all 5 Great Lakes of North America combined. Titan is Saturn's largest moon, and the second biggest moon in the solar system. In fact, it's even larger than the planet Mercury. The 5,150-kilometre wide world is 50% bigger than the diameter of the Earth's moon and 80% more massive. But what really makes Titan unique is that it's the only world in the solar system other than Earth where clouds form rain, which falls onto the ground, forming rivers and streams, which eventually flow into lakes and seas. But unlike Earth's water-based hydrological cycle, Titan's rains are made of methane and ethane. On Titan, temperatures are so cold the water's frozen solid, so hard it forms bedrock. Titan's atmosphere is about 10 times as thick as the Earth's, and it's primarily nitrogen laced with methane and ethane. It all forms a dense golden hydrocarbon haze high up in the Moon's stratosphere. And far below lies the swirling, wave-covered surface of Kraken Mare, Titan's largest sea. After sifting through data from one of Cassini's final Titan flybys, astronomers reporting in the Journal of Geophysical Research were able to determine that Kraken Mare is at least 300 metres deep. The study's lead author, Valerio Poggiali from Cornell University, says the depth and composition of each of Titan's seas has already been measured, except that is for the largest, Kraken Mare, which is not only a great name, but also contains about 80% of the Moon's total surface liquids. The data was gathered on Cassini's T-104 flyby of Titan on August 21, 2014. The spacecraft's radar surveyed Leggera Mare, a smaller sea in the Moon's northern polar region, to look for the mysteriously disappearing and reappearing Magic Island. Then as Cassini cruised by at 21,000 km per hour, nearly 1,000 km above Titan's surface, the spacecraft used its altimeter to measure the depth of both Kraken Mare and Moray Sinus, an estuary located at the sea's northern end. The study's authors, along with engineers from NASA's Jet Propulsion Laboratory in Pasadena, California, had already figured out how to discern lake and sea depth by noting the radar's return time differences on the liquid surface and the sea bottom, as well as the sea's composition by acknowledging the amount of radar energy absorbed during transit through the liquid. It turns out Moray Sinus is about 85 metres deep, shallower than the depths of the central Kraken Mare, which was too deep for the radar to measure. Surprisingly, the liquid's composition, primarily a mixture of ethane and methane, was methane-dominated, and similar to the composition of nearby Leggera Mare, Titan's second largest sea. Earlier, scientists had speculated that Kraken may be more ethane-rich, both because of its size and its extension into the Moon's lower latitudes. The observation that the liquid composition isn't markedly different from the other northern seas is an important finding and will help in assessing models of Titan's Earth-like hydrological system. But there are still many puzzles about this strange moon that remain, one of which is the origin of its liquid methane. See, the amount of sunlight Titan receives is about 100 times less intense than on the Earth, and this should be consistently converting the methane in the atmosphere into ethane. The overall cycle should take about 10 million years, so the process should by now have completely depleted Titan's surface methane reserves. Yet, as this study shows, there's still an ocean worth of methane out there, or at least a sea's worth. This is SpaceTime. Still to come, a new idea about the birth of the solar system, and the first Atlantic splashdown of a CRS Dragon cargo ship. All that and much more still to come on SpaceTime. Okay, let's take a break from our show for a word from our sponsor, Namecheap.com. As their slogan says, search and buy domains from Namecheap at the lowest prices. Now, this is the service that our team at Bytes.com use to buy and manage our domain names, and we're really happy with the service support and value we're getting. Buying the right domain name shouldn't be hard, and with Namecheap, we've found it to be anything but that. And you can find your dream domain and join over 2 million happy customers when you register with Namecheap. Trusted with well over 10 million domains, you'll know you're in safe hands when it comes to turning your website idea into reality. And they've got some excellent tools to help you find the right name, like the handy search engine. All you do is type in your desired name, cross your fingers, and press search. And if what you want's already gone, and it does happen sometimes, they'll come up with some great alternative ideas. And if you're looking for some new inspiration, try the new website domain name finder, Beast Mode. It'll help you discover thousands of domain names fast. We've found their prices to be excellent, management tools intuitive, and they're easy to use with excellent custom support if you need it. All in all, it's a great experience all round if you're looking to pick up a domain name or two. So, why not check them out and help support our show at the same time? Just visit spacetimewithstuartgary.com/namecheap. That's spacetimewithstuartgary.com/namecheap, and Namecheap is one word. You'll find the URL details in the show notes and on our website. Just visit the support page. That's spacetimewithstuartgary.com/namecheap. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
A new study proposes that our solar system was formed through a two-step process, but not quite the way the Nice model and the Grand Tack hypothesis suggest. The Sun and its family of planetary objects, asteroids and comets were formed around 4.6 billion years ago when a massive molecular gas and dust cloud collapsed, causing internal pressures and temperatures inside the cloud to dramatically increase, eventually getting so hot it triggered nuclear fusion at the centre, giving birth to probably hundreds if not thousands of stars all at once, and one of those stars was our Sun. Gas in the protoplanetary nebula surrounding the nascent Sun condensed into droplets and grains of different chemicals, depending on their distance from the Sun. These were gradually drawn together through electrostatic charges to form larger and larger clumps, which, under their own growing gravity, eventually accreted to form planetesimals and ultimately the planets and moons we see today. At the same time, the Sun's rotation caused the surrounding protoplanetary nebula to gradually flatten out into a disk. The rubble left over from the planetary formation process is still with us today as the asteroids and comets we see flying through the solar system. There are very clear demarcation lines where different elements can condense out of the protoplanetary nebula, such as the snow line, marking the boundary between the relatively small rocky terrestrial inner planets, Mercury, Venus, Earth and Mars, and the much larger, colder gaseous outer worlds of Jupiter, Saturn, Uranus and Neptune, which orbit where volatiles tend to form ices rather than liquids. For years, there's also been growing evidence that planetary systems, including our own solar system, aren't stable, but are subjected to a process of planetary migration. You see, a lot of planets contain materials which are unlikely to condense out of the protoplanetary nebula at their current orbital distances from their host stars. Observations of exoplanetary systems have found evidence of numerous giant Jupiter-sized gas planets, so-called hot Jupiters, circling so close it takes just a few days or even hours to complete each orbit around their host star, environments which are far too hot for planetary formation. These planets must have formed further out, and then migrated inwards to their present locations. And astronomers see evidence of similar planetary migration in our Sun solar system as well. The Nice model and variations of it, such as the Grand Tack hypothesis, have been developed to explain specific features, such as the composition of bodies in the main asteroid belt between Mars and Jupiter, and features of the more distant Kuiper belt and Oort cloud. It also explains an event known as the Late Heavy Bombardment some 3.9 billion years ago, the apparent swapping of orbital positions between Neptune and Uranus, and Jupiter's family of Trojan asteroids. The Grand Tack hypothesis suggests that Jupiter underwent a two-phase migration after its formation 4.6 billion years ago near the snow line about 3.5 astronomical units out from the Sun. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. After clearing out a gap in the protoplanetary disk where it formed, Jupiter began migrating inwards to about 1.5 astronomical units, before reversing course and migrating outwards again. If uninterrupted, this migration would have left Jupiter in a close orbit around the Sun, like recently discovered hot Jupiters in other planetary systems. But then along came Saturn. Saturn also migrated towards the Sun, but being smaller it migrated faster, converging on Jupiter and being captured in a 2-3 resonance with Jupiter during its migration. A gap in the protoplanetary nebula then formed around Jupiter and Saturn, altering the balance of forces on these two planets, which began migrating together. Saturn partially cleared its part of the gap, reducing the torque it exerted on Jupiter by the outer gas disk as Jupiter reached between 1.5 and 2 astronomical units out from the early Sun. Now all this caused the net torque of the two planets to become positive, and they began migrating outwards. This outward migration continued because interactions between the planets allowed gas to stream through the gap, exchanging angular momentum with the planets during its passage, in the process adding to the positive balance of torques and moving mass from the outer disk to the inner disk, thereby allowing the planets to migrate outwards relative to the disk. The transfer of gas to the inner disk also slowed the reduction of the inner disk's mass relative to the outer disk as it accreted onto the Sun, allowing enough material to remain to form the inner terrestrial planets Mercury, Venus, Earth and Mars. The outward migration of Jupiter and Saturn continued until they reached a zero-torque configuration within a flared or dissipated gas disk at or near Jupiter's current orbit, some 5.2 astronomical units out from the Sun. Jupiter's Grand Tack also resolves the Mars problem by limiting the amount of material available to form Mars. See, some simulations of the formation of the terrestrial planets end up with Mars being similar in mass to the Earth, instead of its actual mass, which is just a third that of the Earth. Jupiter's inward migration alters this distribution of material, driving planetesimals inwards to form a narrow, dense band, with a mix of materials inside 1 astronomical unit, thereby leaving the Mars region largely empty. Planetary embryos quickly formed in this narrow band, forming the two larger terrestrial worlds, Venus and Earth, over a period of just 60 to 130 million years. The remaining scattered material left outside this band eventually formed the two lower-mass terrestrial planets, Mars and Mercury. The model also demonstrates how Jupiter and Saturn drive most asteroids from their initial orbits during their migrations, leaving behind an excited remnant derived from both inside and outside Jupiter's original location. Before Jupiter's migrations, the surrounding regions would have contained asteroids which varied in composition with their distance from the Sun. Rocky asteroids dominated the inner region, while more primitive and icy asteroids dominated the outer regions beyond the snow line. But as Jupiter and Saturn migrated inwards, about 15% of inner asteroids would have been scattered outwards, flung into orbits beyond Saturn. Then, after reversing course, Jupiter and Saturn again encounter these objects, scattering about 0.5% of the original population back towards the inner solar system into stable orbits. The encounters with Jupiter and Saturn leave many of these captured asteroids with large eccentricities and inclinations. And some of these icy asteroids are also left in orbits crossing the region where the terrestrial planets would later form, thereby allowing water to be delivered to the accreting planets through asteroid impacts. The absence of any close-orbiting super-Earths in our solar system could also be explained as a result of Jupiter's inward migration, which captured planetesimals, causing catastrophic collisional cascades, with the resulting debris spiralling inwards towards the Sun, taking any forming super-Earths along with them. The 4 existing terrestrial planets would then have formed out of the remaining debris left behind when Jupiter and Saturn migrated back out. The Nice model and Grand Tack variation are the best explanation we have to date for the formation of our solar system. But now a new study claims there's another possibility. The new report in the journal Science claims to explain several key features of the terrestrial inner planets, as well as the gas giants of the outer solar system, and even differences in different families of asteroids. The authors from the University of Oxford, LMU Munich, ETH Zurich, BGI Beirut and the University of Zurich base their conclusions on observations of planetary formation in other star systems, combined with laboratory experiments studying the isotope, iron and water content of meteorites. They hypothesized that the inner terrestrial protoplanets accreted early and then dried out due to internal heating by strong radioactive decay. Now, if correct, their idea has several implications for the distribution and necessary formation conditions of Earth-like exoplanets. Their observations of planet-forming disks around other stars show that disk midplanes is where planets form, because these areas have relatively low levels of turbulence, resulting in interactions between dust grains embedded in the disk gas and water around the orbital location where it transitions from a gas to an ice. Now, they say all this triggers an early burst of planetesimal formation in the inner planetary system and then a second later burst further out. They claim the different formation time intervals mean their internal heat engine from radioactive decay also differed substantially. Their simulations suggested the inner terrestrial planets quickly developed magma oceans and eventually differentiated into an iron core and separate mantle, with most volatiles degassing into space, resulting in dry planet compositions. The authors claim that because the outer solar system planetesimals formed later according to their model, they experienced substantially less internal heating, and therefore limited iron core formation and limited volatile gas release.
I am Tim Lichtenberg from the University of Oxford, and I'm excited to share the key results of our research with you. We have worked on uncovering the deep past of our own world and how the solar system came into being. To do so, we connected recent findings from astronomy and geochemistry, and found an internally consistent scenario that explains many properties of the solar system at present day. A novel insight from our work is that the solar system formed in 2 distinct episodes. The first of these episodes had already started when the Sun was still forming. At that time, the inner terrestrial planets started accreting. The second episode started approximately 500,000 years later, when the building blocks of the outer planets formed. Because of the delay in formation time, the outer planets inherited a much smaller amount of radioactive isotopes than the inner planets. The radioactive decay strongly heated the inner planets, but not the outer planets. The inner planets therefore melted, formed iron cores, and lost their initial volatiles, such as water, very quickly. The result of these events is that the inner terrestrial planets today are relatively dry, while the outer ones are rich in volatiles and water. Let me summarize a few key aspects and highlights of our work. We performed computer simulations that show that the formation of the solar system can be explained by the mentioned 2-step process. The inner planets started first but accreted slowly. The outer planets started later but accreted more rapidly. This is because of the movement of the so-called snow line in the solar accretion disk. The snow line is the location of the gas disk where water ice transitions from being the gas to ice phase. The sequence of astrophysical formation effects and geophysical evolution explains the split in water content of the inner versus the outer solar system, and reproduces the formation chronology that is recorded today in meteorites. In particular, it reproduces the time clustering of iron core formation and water rock reactions that we observe in meteorites, and the difference in isotope composition of extraterrestrial materials from the inner and outer solar system. In this new theory of solar system formation, the terrestrial planets are dry because of their timing of accretion and the inventory of radioactive isotopes that got incorporated into their earliest building blocks. Specifically, the short-lived radioactive isotope aluminum-26 heated planetesimal interiors on a timescale that is comparable to the timescale of planetary accretion. This is different from the classical scenario of solar system formation, in which the initial building blocks are thought to be formed at roughly the same time in the whole disk. In this classical view, the difference in volatile and water content is usually explained with the static position of the snowline. In contrast, in our new scenario, the snowline movement consistent with astrophysical models is important to trigger planetesimal formation bursts at different times and locations. This new solar system formation scenario gives some insights into the relational place of Earth and the solar system relative to extrasolar planetary systems. Because the inventory of volatile elements in the Earth is a result of the specific chronology and path of accretion, exoplanetary systems should show strong variations in atmospheric and climate state compared to our own world. For example, the Earth is dry because of the inventory of radioactive isotopes in the early solar system, but other planetary systems likely have very different inventories of these radioactive isotopes. And so, the geophysical evolution of planets in these systems takes a different path, resulting in, for us, seemingly exotic compositions and climates.
This is SpaceTime. Still to come, the first Atlantic splashdown for a CRS Dragon cargo ship, and China's first rocket launch of the new year. All that and more coming up on SpaceTime. The SpaceX CRS-21 Dragon cargo ship has successfully returned to Earth, loaded with returned experiments from the International Space Station. However, unlike previous returns, which have usually splashed down in the North Pacific Ocean off the coast of Baja California, this latest mission splashed down in the North Atlantic off the coast of Florida. The Dragon CRS-21 spent a month docked to the space station. The mission was the first to use the new upgraded Cargo Dragon 2 capsule, which is twice the powered locker capacity of the earlier first-generation Dragon cargo ship, thereby allowing more research to travel back to Earth for analysis. 3 of the projects returning to Earth on this mission were funded by the National Institutes of Health through the Tissue Chips in Space initiative. Tissue chip research included heart disease, post-traumatic osteoarthritis, and a muscle atrophy experiment. Also returning was an investigation using a brain organoid model to study neurological diseases such as autism and Alzheimer's. Another experiment demonstrated the manufacture of a single-piece turbine blade disc combination in microgravity for use in the aerospace industry. Building them in space could result in parts with lower mass, less residual stress, and higher strength than those manufactured on Earth. 2 separate studies looking at the production of optical fibers in microgravity were also included in the payload. Another experiment evaluated the effectiveness of silver-based disinfectant on bacterial films. Then there was a study on how microgravity changes the structure of blood vessels in the eye, and an experiment examining the expression of circadian genes which regulate sleep and wakefulness in space, following reports by some astronauts of cognitive changes following spaceflight. This is SpaceTime. Still to come, China's first rocket launch of the new year, and later in the science report, a new study shows that once COVID-19 symptoms begin, the virus tends to hang around infecting others for at least 7 days. All that and much more still to come on SpaceTime. China has successfully carried out its first rocket launch for 2021, placing a new mobile telecommunications satellite into orbit. The Tiantong 103 was launched from the Xichang Satellite Launch Center in southwestern China's Sichuan province aboard a Long March 3B rocket. The satellite will provide mobile telecommunications over a footprint covering China, as well as the Middle East, Africa, and most of the Indian and Pacific Oceans. The flight represented the 358th launch of a Long March series rocket. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study claims that once COVID-19 symptoms begin, the virus is live and can grow for around 7 days, with people capable of testing positive for up to 34 days. Current COVID-19 tests look for viral genetic material rather than live virus. So researchers from South Korea were keen to see how long people actually shed live viruses that could be grown in culture. Their study, reported in the New England Journal of Medicine, found that the longest gap between symptom onset and the ability to grow a live virus was 12 days. The authors say their findings are useful in guiding isolation periods for patients with COVID-19 and for estimating the risk of secondary transmission among close contacts in contact tracing. The virus, which is believed to have accidentally escaped from the Chinese Academy of Sciences Wuhan Institute of Virology laboratory in the last quarter of 2019, has now killed some 2.3 million people and infected over 105 million others. A new study has found that elderly people who get the flu seem to produce fewer immune emergency signals from infected cells, which in turn slows their immune response to infection compared to younger people. The findings, reported in the Journal of Clinical and Translational Immunology, show that as people get older, they start to lose immune T cells, which is specific for combating the flu virus. The research also found that regardless of age, people infected with COVID-19 didn't produce the emergency signals needed for an early immune response to the virus. The authors suggest that's because COVID-19 is a new virus and people simply haven't encountered it before, so there are no specific immune cells to fight it. A new study warns that the number of sharks and rays worldwide has fallen by 71% since 1970. The findings, reported in the journal Nature, show that more than 3/4 of shark species are now threatened with extinction, including the oceanic white-tip shark and the scalloped and great hammerhead sharks, which are now classified as critically endangered. Researchers say that the decline is related to significant overfishing of shark and ray populations, and governments need to implement strict science-based catch quotas now in order to help promote species recovery. A new study shows that while you may have a pretty good idea of how drunk you are after the first 2 drinks, things tend to get a bit more iffy once your alcohol consumption increases beyond this level. A report in the Journal of Drug and Alcohol Review suggests that once your blood alcohol level gets to around 2 to 3 times the Australian legal drink driving limit of 0.5%, you probably underestimate how drunk you really are. The study also found that people are more likely to underestimate the intoxication of older people. In other words, the oldies are sneaky and cunning and able to hide it better. Google has threatened to cut off Australia's access to its search engine and email services if the federal government goes ahead with its news media bargaining code legislation, which would force Google and Facebook to pay for the news content they use. Google's Australian head Mel Silver claims the legislation is an untenable risk to the tech giant. That's despite making $4.8 billion in revenue from its Australian operations last year, while paying just $59 million in corporate tax. The tech oligarchs, Google, Facebook and Twitter, have already been exposed as politically manipulative, deliberately withholding legitimate news and willing to suspend or shut down the accounts of anyone who doesn't agree with their political viewpoint. Poland is introducing legislation to make it illegal for social media companies to suspend or shut down accounts unless the comments contravene Polish law. And Florida Governor Ron DeSantis is introducing new legislation in his state to fine tech oligarchs when they deplatform political views they don't agree with. There are also growing calls for the United States to remove Section 230 protection, thereby treating tech oligarchs as the publishers they are rather than the service providers they claim to be, in the process leaving them open to the same laws and defamation actions as other media publishers. Alex Zaharovoit from ITY.com says it's a sign of the times.
In France, Google has signed a deal with French publishers to pay French news organizations who are part of something called the Google News Showcase, a licensing payment of some sort to provide Google's users access to what they call enriched content. And it's assumed that if this deal goes through, then Google will have to start paying other European countries and the publishers some form of payment for being able to link their news. This Google News Showcase is something that they brought about in the 1st of October last year. It's a way that Google can pay for news, but on its own terms. I mean, Google themselves are saying that if they have to start paying to link things. That's the way that search engines have worked for 20 years. And if they start having to pay news organizations, who are they going to have to pay for links next? And it's the case that news organizations have benefited from a lot of traffic that Google has brought to those publications through Google News.
Yeah, but the problem there is the advertising benefits haven't come through. Google have held on to those, and the people who are actually generating the news, writing it and researching it and reporting it, they're missing out on all that money.
Yeah, well, I mean, they are and they aren't. I mean, in one sense, if Google is sending readers your way to your website, well, then those readers are seeing the ads on your site. But of course, Google makes a lot of money themselves through the ads around the whole search process. Not that I see many ads or any ads on the Google News section of Google's website. But in the traditional Google section, yeah, there are ads all over the place. Google owns DoubleClick, and the rivers of gold that were the classified ads of newspapers from 20 years ago have all dried up, and even things like Yellow Pages, they're a shadow of their former selves. It all goes to Google and Facebook and, these sorts of huge sites that have huge amounts of traffic and huge amounts of eyeballs. And, of course, news is very expensive to produce. You've got to pay journalists. I mean, there's been huge cutbacks in the news industry. There are no more sub-editors anymore. You often see, even on major news sites, articles littered with typos and spelling errors. I remember somebody telling me that there was once 3 pairs of eyes that saw an article before it got published in a magazine. But those days are long gone. And I don't know if forcing Google to pay is going to bring all of those people back. I mean, it won't. Obviously, the economies of scale have shifted dramatically in the news business. Journalism, being a writer, is not the path to riches. Being a publisher is no longer seemingly the path to riches either. I mean, owning a search engine or a major social media network seems to be that path to riches. But you try starting up your own or a competing social media network, and you'll find it's not so easy. And if you don't have the correct political beliefs, you might be shut down. The world has changed. We're yet to see what's going to happen for real in Australia. The government and Google are still fighting. But given the fact that Google was able to come to some sort of deal with the French, perhaps, both sides have to give leeway, have to give way of some sort. But what that's going to be is saying Google is threatening to shut down Google search in Australia completely if they're forced. And, if that happens, then, Australians will be forced to use a VPN to get access to Google.
That was my initial plan. As soon as I heard that, I thought, oh, well, that's okay. I'll just go through my VPN.
But, what would it mean, for example, for Gmail? I have my email address hosted at Gmail. I gave up on Microsoft Outlook many years ago because it was just too fiddly dealing with PST files and corruptions. And it was great to be able to have the same email on every system I use without having to deal with IMAP servers. So if Google did disappear from Australia, it would be a pretty terrible thing. Both sides have power. I mean, Australia says, well, we make the laws for how companies operate in Australia. And there are people who are telling Google and Facebook that this is the way they want to behave. They should go. There's an organisation called Reef Australia, and they have put together a series of demands that were basically saying that this shows that Google's egregious threats, they say, prove regulation is long overdue. And, the executive director of Reset Australia, Chris Cooper, said that when a private corporation tries to use its monopoly power to threaten and bully a sovereign nation, it's a surefire sign that regulation is long overdue.
What do you think? Are these carpetbaggers and racketeering that needs to be put under control, finally? Get the tech oligarchs to toe the line?
Both sides are going to want to play tough and want to see who blinks first. There has to be some sort of common ground that they can reach. Google will most likely have to pay news publishers. But if they're paying the big news publishers, what about small news publishers? What about the organization I write for? Are we going to get paid by Google? Or is Google going to say, no, we're only going to pay the major publications in Australia and the rest of you can either be damned or get nothing and just be happy for the traffic? So I don't know who's going to win this one. I think that the ripping off of content without some sort of recompense is probably coming to an end.
That's Alex Zaharov-Reut from ITY.com. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTimeWithStuartGary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.